93 million miles from the sun, is the pathway of Earth. Beyond here is planet Mars and 5 other solar worlds that man dreams of knowing. Perhaps man will never reach to the wilderness of stars, but he dares now to begin the exploration of his own solar system. When I first arrive in Pasadena at the Jet Propulsion Laboratory, I want to ask, why are we exploring the planets? Before the conference, we talk with Dr. William H. Pickering, director of JPL. In matter-of-fact terms, he introduces the coming greatest adventure of man, a search for life on other worlds.
The long-range purpose of unmanned exploration of the planets is the development of technology which will lead to eventual manned exploration. Scientifically, our objective is to assist in answering 2 basic questions. What, if any, life forms exist on the planets, and how has the solar system been formed?
We have ignition and liftoff of a Delta II rocket carrying NASA on an Odyssey.
When I was a kid, when I was in high school, the picture of the solar system was very, very different from what it is today. And it's the JPL missions that have gone to, Magellan to Venus, and the different missions to Mars, and Voyager and Galileo at Jupiter, and Voyager out beyond that have changed that. I mean, they've really changed that picture.
JPL is involved in some of the toughest technology that can be even dreamed of. There are things that JPL does best, nobody can do them better. They have special talents in robotics, rovers on planets, navigation, communication. JPL is a cornerstone of our Mars program. Partially it's in-house at JPL, but it's also
to prediction.
The Earth is extremely dynamic, down to plate tectonics, to earthquakes, to the core. We can measure volcanic eruptions, but we can measure what goes on before and after a volcanic eruption. We can do the same with earthquakes. We can measure earthquakes, and we can measure how things change before and after earthquakes. And this is very exciting. We no longer are only just measuring the shaking part of the earthquake or looking at the geologic record. We're actually measuring the Earth as it moves, as strain builds up, as stress builds up, and we can watch that break. So we can see the entire earthquake cycle for the first time. Ultimately, we'd like to forecast earthquakes or predict earthquakes. It will certainly help us understand the earthquake hazard better. The thing that's really exciting to me, especially where I am right now at JPL, is we can take one technique for studying the universe and apply that same technique to the Earth.
Once you're out there on your way to a planet, you are on your own. Mars has consumed about 50% of the vehicles that humans have sent to the planet for exploration. It's incredibly hard to explore, and the surface is doubly so.
Don't think things won't go wrong. Things will go wrong. Anything, as soon as you ever find yourself saying that won't happen, it might.
It's scary, When you do one of these projects, you put years of your life, many years of your life, your heart, your soul, your passion, everything that you care about into them. And when they succeed, it's the greatest feeling in the world, and when they fail, it's just one of the worst feelings in the world. And when you do this, yeah, it's frightening. It's frightening.
They feel, particularly my wife, is as committed to this as I am. I mean, she, in a sense, when it came down to, do I want to work on MER? Do I want to try, work on the 2000 entry? Because we knew it was going to be very difficult and a lot of work. She was the one that was sort of almost pushing me. She's like, we want to go. I mean, she's like, I want to be a part of a success again as well.
We are sending brand new spacecraft to the planet every 26 months. Each of those spacecraft is finely tuned to studying an aspect of the planet. So it is the advancement with each mission of our knowledge and the tailoring of future missions based on what we learn today that makes Mars unique.
We have compelling evidence that Mars was once warmer, was once wetter, was once more Earth-like than it is today. We think. We see from orbit stuff that makes us think that. What we want to do is we want to understand how warm, how wet, what were the conditions really like? Were they the kind of conditions that could have supported life?
And water is a key. Our present understanding of life and its development suggests that if there's no water present in a persistent form, meaning lakes, ponds, flowing rivers on Mars, then the probability that life would have developed on the surface is very low. So water becomes a very important part of our exploration of Mars. We think that the evidence of the history of water on Mars does sit right at its surface, ready to be picked up.
So what we're doing is we're sending 2 robotic field geologists to the 2 most interesting places that we can find that are safe enough for us to land. By interesting, I mean places where there's evidence that water was there.
Our landers with wheels, they will stand up and walk off and explore and go out and drive off toward the horizon and explore places and scenes that no human has ever seen before. We're loaded with cameras. We have cameras in the front of the rover, we have cameras in the back, and we have cameras sitting up on a mast in stereo that allows us to be able to see the scenes around us in much the same way that a human being would see them standing there on the surface of Mars.
These machines do our exploring for us. They become extensions of ourselves. We build them with brains. We build them with eyes. The MER rover has an arm that's like exactly the same dimensions as my arm, same length, elbow, wrist, shoulder, okay? We build them to do our work for us, and you can't. You simply, if you got a heart beating in your chest, you cannot pour the energy into these vehicles that we do and not become attached to them emotionally. I mean, I can't help it. I cannot avoid that. I don't try to. Okay, I mean, I love those rovers.
Time, Houston. The spacecraft is stable. Galileo is on its way to another world. It's in the hands of the best flight controllers in this world. Fly safe.
Galileo had a actually fantastic history because it was a mission that had to go through a lot of hurdles to actually happen. It was nearly cancelled after the explosion of the Shuttle Challenger. A new trajectory had to be worked out to get Galileo from Earth to Jupiter because we missed the launch window that would take us directly to Jupiter. So we went all over the solar system. We went to Venus first and got a gravity assist, went to the asteroid belt, came back to Earth, got another gravity assist, went back to the asteroid belt, came back to Earth a second time, and finally got to Jupiter in 1995.
I think for myself, the things that interest me the most about Jupiter are the things that we don't understand. A place like Io, which is one of the large Galilean moons, where volcanoes are going off all the time. We have a place like Europa, where there's this very smooth, icy surface, underneath which there may actually be a liquid ocean, and there's even a possibility of life. Okay, you have a moon like Ganymede, which has an iron core that's very much like the Earth's in that it produces a magnetic field. It's the only planetary moon that seems to produce its own magnetic field. That is still an active planet. It's still working.
We learned just mind-changing things. Every time we went by the moon Europa, the estimates of its age began to drop dramatically. Oh, it's not 3 billion years, it's 1 billion years. And then, it's several hundred million years. The crater count seems to show that it could be 10,000 years. You know, I mean, it just dropped until now we're thinking that, well, maybe it's still active. Maybe there's a layer of liquid water under there that might be relatively close to the surface. Maybe there's an appropriate environment suitable for some sort of extraterrestrial life. I mean, this is just, it was science fiction. We started out, we went there in what they called an exploratory mode. We don't know anything and we're just there to see what we can see. And what we learned was phenomenal. So it was that was the style of mission that it was, and was, definitely worth its weight in gold.
Everything. What is there not to like about Saturn if you're a planetary scientist? Rings separate Saturn from all the other planets. The rings give Saturn its unique quality. We have a gas planet, the second biggest planet in the solar system. Saturn is the only planet in the solar system whose density is less than that of water. You know what that means? That means if you had a bathtub big enough, this planet would float. It would, of course, leave a ring. Cassini is the last of the Cadillac missions. It's the last of the very big spacecraft, very capable spacecraft. This is the biggest and most capable spacecraft we have ever sent into deep space. It has 12 science instruments on board, more than any other spacecraft. We're expecting to get some fantastic images. We have 30 and counting known moons, and we have Titan, the only moon in the solar system with an appreciable atmosphere. Titan from a distance, Titan from even up close, looks like a big basketball. You could write Voight across it and you could be convinced it was a basketball. The Huygens probe is the first mission that we have sent, which is designed to float. If there are lakes of liquid ethane and or methane, which we think there are, this thing will float and hopefully will survive splashdown or landing to send back data from the surface of Titan. After orbit insertion, which occurs over the rings, we try to avoid the rings as much as possible. We treat them as a collision hazard. So we spend a lot of effort making sure the spacecraft will be at the right orientation to pass through areas of particles so it doesn't get damaged. We treat the rings very seriously. You go into this job, you know that I could lose my spacecraft today, and all the work I've done in the past 6 years could be gone tomorrow. But that's what you accept by doing this job. If you're a football player, you accept when you go on that field that you could lose that day. You don't gain things without risking things. You don't gain valuable things without some risk.
My current mission is called Deep Impact. The mission is to fly to a comet, Comet Tempel 1, to impact the comet with a small spacecraft, then observe the impact event. It'll create a crater, we believe about the size of a football field. We have, from the time of impact to the time the comet basically flies by us, flies by the flyby spacecraft, we have 13 minutes. Once it hits, we see this incredible cratering event, and for the next 13 minutes, as the comet keeps coming at the flyby spacecraft, we're taking pictures and sending those down as fast as we can. Comets are the most mysterious objects in the solar system. We know less about comets than anything else in the solar system. We don't really know what the internal composition of a comet is. And there is a theory that says that after the Earth cooled, there was continual bombardment from comets and other bodies throughout the solar system, but that the comets could have seeded the Earth with organic materials, as well as provided a lot of the water that became our oceans. So those are all theories, and it'll be some time before we can resolve them. But understanding the structure, the composition, and how comets formed will help us understand that.
Your mission was the first one to go and explore an asteroid. Something that scientists have been waiting to do for decades. Asteroids are the building blocks of the planets, at least the inner planets, like the one that we live on. NEAR was not only the first spacecraft to orbit an asteroid, it was also the first spacecraft to land on an asteroid. It was never designed to do that. So those of us who worked on the mission from the very beginning said to ourselves, we have to land on this asteroid. We just have to do it. We partnered with the JPL navigation team, who had a very daunting task, is to control and to navigate a spacecraft while it was in orbit around an irregular body. This has never been done before. We didn't even know if it was really possible. This was a challenge that the JPL navigation team had to face, and they developed the techniques from nothing. In the end, the mission was operated without a hitch. It just went perfectly.
One of the most wonderful stories that's happening in JPL right now is this idea that we're no longer just looking at the planets in our own solar system, but now JPL is really taking the lead in finding planets outside our solar system. And we'll actually be able to see solar systems as a whole. We'll be able to see this warm dust going around a star. And then once SIRTIF has identified hopefully hundreds, maybe even thousands of new planetary systems, then it'll be usually the interferometers that'll come along with their wonderfully clear vision, and they'll be able to see planets in those solar systems. We're going to be able to see, in the case of SIM, maybe something like Jupiter, a larger planet going around a star. But then as we slowly move out to the terrestrial planet finder, we'll be able to detect, as the name suggests, terrestrial-like planets, Earth-like planets very close in to their parent stars. So there's a wonderful progression. You know, JPL was the expert, we were really the experts in exploring the solar system, and now we're becoming the experts in new solar systems. And what we're going to find out there just boggles the mind. Humans are looking for our origins. We're looking to see where we came from and how our own solar system formed. We're searching for ourselves out there. You know, we're searching to find how we first came into being. And so I think that this quest for a little blue dot, you know, that tiny Earth-like planet, it's so difficult to find. But because we haven't found it yet, we haven't found our kindred spirits out there. We haven't really found our brothers yet, and we know they're there. And I've gone all over the country, and I've had people literally standing in line to ask me a question. What is a black hole? Or what's the nearest galaxy? Or do you believe there's life outside our planet? They're telling us we need to do a better job bringing it to them, because that's really what we're for, right? I mean, if scientists can't enrich the rest of society by the discoveries they make, what is this for? This is theirs, not just something away in space. This is their story too.